Okay, so in these lecture slides, we're going to find the curl and divergence of the magnetic field, and also we're going to be introduced to Ampere's law. So the first thing that you're going to do is example problem 5.5, where I want you to find the divergence of a magnetic field. And I've kind of laid out the steps on how to do that here. You start with Biot-Savart law, and then you're going to need to use the divergence, take the divergence of both sides, and then use this vector ID. What you'll find is that the divergence of a magnetic field is 0. And this is another way of saying that there are no magnetic monopoles. Okay, so if you take a magnet, you have a north and south pole to that magnet. So any magnetic field lines leaving a surface enclosing that magnet will come back in the south pole on the other side. And you can't cut this in half. If you cut this magnet in half, you'll just get another north and south pole. So the divergence of B is an expression of the fact that there are no magnetic monopoles in nature. Now I want you to find the curl of a magnetic field. It's a little longer process, but I give you the steps on how to do that here. What you're going to find is Ampere's law, which states that the curl of a magnetic field is equal to the current density times the probability of free space. Okay, so you have current, the magnetic field created that by that current, you can find by using the divergence of that magnetic field will equal that current density. We can also write Ampere's law in integral form. So if we start with Ampere's law in differential form that we just found, the curl of the B field is mu naught times J. We take the surface integral of both sides. We're going to use Stokes' theorem on this left-hand side. We have the curl of a surface integral. That's going to be equal to the line integral going around that surface of that vector field. And if we take the integral of the right-hand side, we have a current density times dA. That just gives us the current enclosed in that area dA, in that area A. So we find Ampere's law in integral form that states that the line integral of the B field around a surface equals the current enclosed in that surface. So now that we know Ampere's law, I want you to now recalculate the magnetic field generated by an infinite straight wire that we calculated last lecture slides using Biot-Savart law, this time using Ampere's law. You'll see it's an easier calculation, but you should end up with the same result. Then I want you to find the magnetic field using, again, Ampere's law of a solenoid. And then we will do some clicker questions. And that is it.